been edited many times. Okay, so the first thing you need to understand is that we started the chapter with two basic questions. The first question was, does this series converge? And then the second question was, if it converges, what does it converge to? And I told you that we would not be able to answer that second question every time. Just can't do it. It's too hard to answer. So most of the time, we don't even answer the question, what does it converge to? We just answer, yes, it converges by the direct comparison test. Okay? But we also need to still talk about when something converges and when it doesn't, and how we can know a convergence value. And we should know that we don't know the convergence value. Okay? We should know how far off we are if we guesstimate a convergence value, that sort of thing. Okay? So I want to start out really simple on this. Here's the two basic things you need to take from page 1. If it's an infinite series, right, and it happens to be geometric, okay, and it happens to have an r less than 1, not only does it converge, but we can find the convergence value. Okay, for example, this problem. In this problem, you have this little pattern, right? Technically, it should be pluses in there, not commas, because it says series. Let me put those in. Can you see what I'm multiplying by each time? Yeah, the top is being multiplied by negative e, for sure. That's why it keeps going up in degree by e, and it keeps changing signs, right? The bottom is going basically rad 2, 3 rad 4, 9 rad 8, 27 rad 16. It looks like somebody's multiplying the bottom by 3 and by rad 2. In other words, this thing seems to be geometric. It seems to have a first term e over rad 2. That's pretty obvious. Here it is. First term is e over rad 2. Just want to highlight that little guy. It's highlighting the whole thing. Okay, anyway, that little gray thing goes on top, right? First term. And then on the bottom, there's your common ratio. Negative e over 3 rad 2. Since e is about 2.7 and 3 rad 2 is closer to like 4 point something, that is less than 1. It does converge. In fact, we can actually calculate what it converges to. I simplified it for you already. It's 3e over 3 root 2 plus e. Okay, it's very rare when we can do this, when we can actually get a convergence value, but we can do it if it's geometric. Okay, that's point number 1 in the first page. Point number 2, we can also find the convergence value if it's telescoping. We saw this way back in lesson 1 or 2, I forget. Okay? If a series is telescoping, it typically looks like two fractional terms. And if you just simply write out the first few terms, 1 over 1 minus 1 over 3, 1 over 2 minus 1 over 4, 1 over 3 minus 1 over 5, and so on, after writing out the first 6 terms, whatever, you start realizing that things are canceling in pairs, except for a lonely 1 over 1 and a 1 over 2. These guys never got a partner, so they survive the infinite sum. And they are the survivors, and they are the answer. 3/2 is what this must add up to if everything seems to be canceling, except the 1 1/2. Okay? Another way you can look at example 2 here is you can just basically find a pattern in the partial sums. This is extremely hard to do. So I'll go through it again, because we did it the first day. But basically, you can take the first term, which is 1 over 1 minus 1 over 3, and collapse it to 2/3. You can take the second term, which is a half minus a fourth, and collapse it to a fourth. 1/3 minus a fifth is 2/15. 1/4 minus a sixth is 1/12. 1/5 minus 1/7 is 2/35. You see? And then you can form a new sequence. This sequence is called the sequence of the partial sums. And what you do is you start off with A1 as your first term, no big deal, 2/3. But then A2, or S2, the second term, is the sum of terms 1 and 2 from your sequence. So 2/3 plus 1/4 is 11/12. Okay, so I got this 11/12 by adding together A1 and A2. And then to find S3, unfortunately, you have to add 3 things together. And you get 21/20. I just added A1, A2, and A3 from up here. 2/3, 1/4, 2/15. And I did it all the way up to S4. Started out writing your S5 for you. But then you just take a good hard look at this sequence, what do you notice about this sequence? We've got it 2/3, 11/12, so 21/20, so 17/15, etc. Is there a pattern there? Yes, there is. Here's the pattern. 3n squared plus 5n over 2n squared plus 6n plus 4. Don't think I would have guessed that pattern. I got that from Wolfram Alpha. Okay? My point on this is you can see its relationship to the convergence value. When you find its limit, you get the 3/2. So the limit of the partial sums formula is the convergence value. That's good to know, even though it's kind of too hard to do. Okay? So there's two ways to get that 3/2. One, telescope it out, cancel all the stuff, see what survives. Or see if you can create a sequence of partial sums, find an equation for those, and then limit it. Okay? You do not have to do this at all on the AP test. It's too time consuming either way you do it. Okay? I've never seen a telescopic series on the AP test, and neither has Mr. Lynch. Okay? But the concept's important, that this partial sum does exist, or this final sum does exist or doesn't exist, right? Okay, let's go to this page. So the problem on that, of course, well, you guys, this is part of your first page. I think I gave myself a little too much space in here. Yeah, you guys are still page 1 here. The problem is getting the S sub n figured out. Good luck with that, right? We may just use a partial sum instead sometimes. So what does that mean? Well, let's say that we don't want to use, let's say you're studying the series, I don't know, sigma 1 over n factorial, n equals 0 to infinity, right? And just for kicks, let's make it alternate. Okay, so what is this thing? This is 1, and then it's minus 1 over 1 factorial, plus 1 over 2 factorial, minus 1 over 3 factorial, plus 1 over 4 factorial. Since you can't write them all, and you certainly can't add them all, right? How will you even know if you, what they're going to combine to make? Because I believe this converges, but I don't know what it converges to. Is there a way I can sort of estimate that? Okay. Actually, with the alternating, you can sort of estimate, let's say you only go out to, I don't know, first 5 terms, okay? Let's say you stop here because you're too lazy to write anymore, or you realize I can't do this forever. So let's say you just added these 5 together. Obviously, that's not the same as adding all of them together, but how far off are you really? The stuff after this term, that's tiny garbage. I mean, really, really small stuff. Maybe just adding the first 5 terms is good enough for sort of estimating the total convergence value. You see? How far off is the sum of the first 5 terms versus the actual infinite sum? We should be able to answer that question by the end of this lesson. Okay? So if it's an alternating series, you can actually show, I can actually show you that the error on using these 5 terms is no more than 1/100th error from the actual answer. Okay, so I'll show you how to figure that out, and probably end of today or first thing tomorrow. Okay? If you want more accurate, of course, you include more terms. If you go ahead and go out to the next term, and you include that next term, your error will be less than 1 in 500. Okay? If you go even further, you'll have less than a 1/5000th error. So who's going to add them all up? Nobody. But if we add up the first 7, we've already got a really accurate answer. You know, that's the idea. If it's not alternating, then we use a slightly different method to calculate the offness of our partial sum. Okay? So my goal is to show you just a couple ways to do that. Here's a general rule of thumb if you don't have alternating. Okay? You can estimate the value of S by choosing a certain partial sum, let's say the 5th partial sum, and then you can use an integral to figure out how off you are. So let's try it real quick. You don't really need to follow the comments up above. You can just follow the example. It's pretty easy to understand. So this pattern goes like this. 1 squared over e to the first, 2 squared over e squared, 3 squared over e cubed, 4 squared over e to the 4th. And we're doing 5 partial sums, so we'll stop when we reach the 5th fraction, which in this case is the term with 5s in it. That's not always true, but it's true here. This is the first 5 added together. This is called S5, and this has a value. So I actually used my calculator, and I actually typed this in, and I got where's my answer key? Here it is. I don't like typing this stuff, so I'll go ahead and tell you what I got. I got 1.8188. Okay? 1.8188. Here, I'll give you more digits. 030866. So that is roughly what you get when you add the first 5 terms together. Now, is this the same as adding up all the terms? Is that the same thing as adding up all the infinite terms? No. How close? Right, that's the question. How close are we? It's pretty close. It's not as accurate as we could do. Let me show you how close we are. So what you do then is you take s sub 5 plus the integral from 5 to infinity of x squared over e to the x, and you take s sub 5 plus the integral from 6 to infinity x squared over e to the x, and you work these out. Both of these are improper integrals that use tabular integration. So they are both a pain to do. I did them both for you. Actually, Wolfram Alpha helped a lot. And I got, for a final answer here, remember I'm using s sub 5 here, and I'm adding on this extra integral. For this one, I got 2.068107. 12556. Thank you, Wolfram Alpha. And for this one, I got 1.942740694. That's more digits than your calculator might give. It's because I used the computer, not the calculator. So what does this mean? Well, I'm actually kind of done with this value up here, okay? What we're saying is that this infinite sum is something between 1.943 and 2.068. So I did use the 1.8188, but I only used it as a stepping stone. I evaluated the 5th partial sum, and then I added an integral to it, I added a different integral to it, getting me 2 values, and then I'm done with 1.8188. I'm done with that. My answer is between these 2 numbers. I don't really like that margin of error. That's like, that's significant. It's like a 0.05 error or something, and more than I'd hoped. But if I wanted more accuracy, what could I probably have done? Started the problem by doing what?
Go up higher, so like S of 10.
Yeah, I could have gone to like S of 10. More typing, maybe, on the calculator. Once I get that, I would have done integrals from 10 to infinity and 11 to infinity. See? And this margin here would be tighter. Like it would be actually, these 2 numbers would be more similar, which means we're closer to the real deal. You can never quite get the actual convergence value unless you happen to know the partial sums nth term and limit it. See? Clever workaround though. What's your question? Comment?
No, I was just
Okay.
trying to see if it was right.
Okay, so now we know roughly what this thing converges to, which is a question we couldn't answer before. We certainly knew that it converged. Look at it. It's exponential on the bottom, right? It's n squared on top. This is term by term less than something convergent, I'm sure. You could play around with it. Does everyone understand what we just accomplished? It's kind of a big deal. We added an infinite number of numbers together and sort of got a margin of answers there. Okay. So I'll skip the reason why that works. But it's kind of like instead of adding all the little segments together, we kind of added the first 5 together, okay? And then for the rest of this, we found this area and this area. This is the area between 5 and infinity and 6 and infinity. And we added that onto our blue. So we're saying that the answer is between the blue plus the red and the blue plus the black. So I don't want to get too detailed with the sketching, but trust me, this works pretty well. Okay, the AP test has a very, very narrow set of questions that they ask, okay, for error type stuff like this. And so I'm going to try and show you what shows up on the AP test, okay? First thing that the AP test tests every single time is what is the error in truncating and alternating series, okay? So here is the same kind of question we just asked, but you wouldn't probably use integration because it has some negative terms in it, every other term, in fact. So let's just write it out. What is s sub 5 anyway? It's basically negative 1 to the first over 36 plus negative 1 squared over, what's 5? Oh, this denominator is 6, not 36. It's 1 plus 5. I don't know what I just did. The next term is 4 plus 5 on the bottom, see? You plug in 3, you get negative 1 over 9 plus 5. We're only going to go out to 25 plus 5 here. 16 plus 5. And lastly, 25 plus 5. Now we could ask, can we use integration to find the error on this, like we did on the last example? And the answer is kind of no, because unfortunately this series has segments that look like this. Some are above the axis, some are below the axis. So integration is going to be bad because it will have some negative areas, positive areas, that sort of thing. So we don't want to do that. But with alternating series, it's super easy to find the error. So whatever this adds up to, of course, is not the real deal. There are many more terms we didn't use. S includes all of these and many, 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 many more, right? But what is the difference between S, which is the actual convergence value, and S sub 5? What is the error here? Well, the absolute error is just the value of the first neglected term. In other words, if I had continued writing, what would my next term have been? If I had continued writing? 1 over what? 36 plus 5. In other words, my error is no more than 1/41. What does that mean? It means S and S of 5 could not possibly differ by more than 1/41. What is 1 over 41 anyway? Let's check our calculator. What is 1 over 41? Let's see here. 0.02439. 0.02439. You know what this means? It means that we were kind of lazy. We only did 5 terms, but we're already within 2/100ths of the right answer, or 2.5/100ths. We're already really close to the actual deal. Okay, of course, if you want to get closer, then try a few more terms. So notice this one is alternating series. The alternating series remainder is super easy. Just find the next term. That is your error. Interesting. The first unused term is the error in truncating. Let's try the next one. Notice I did not have to actually write S sub 5 to figure this problem out. If I'm going to find the error in using the 7th partial sum, I just need the 8th term. Right? I don't need to do what I just did. Like, forget that. S minus S sub 7 should be less than or equal to A sub 8 is what we're saying. All I need is the 8th term. That is the error in truncating at the 7th term. All right, so let's plug in 8. Negative 1 to the 8th times 8 factorial over 17 factorial. And then there's an absolute value. So So I have 8 factorial over 17 factorial. Question?
Yeah, why is it, okay, so why is it that s minus s sub whatever equals the next term?
It's not equal to, it's less than or equal to the next term. So you want me to explain why the truncation error on an alternating series is always less than or equal to the first unused term?
Yeah, well, I don't know, I just don't
There's a good
understand.
description in our book, it's the whole picture.
I just don't understand how you know s minus s sub 5 is, so yeah, I guess what you said.
That's the rule of the day. So you can just write it like this. S minus S sub k on an alternating series and an alternating series only, okay, will always be less than or equal to A sub k plus 1. It's really interesting. There is a very simple proof for all of this, but I'm not going to try and prove it to you. Just know that if you want to add the first 99 terms together, just how far off are you from the real answer? Well, check the 100th term, because that's your maximum error. Whatever the 100th term is your actual error. Interesting. That only works on an alternating, but I need the answer to that, and I cannot find my calculator. So can someone do me a favor and type 8 factorial over 17 factorial?
Yeah, it's 1.133 times 10 to the negative.
Yeah, and do you guys know where to find your factorial button? It's under math probability. It's the 4th option under math probability. You might want to find that button because you need it for this year's AP test, right? But you're right. You said it was about 1.1336 times 10 to the minus 10th. That means we are like a little less than 2 10-billionths off. Like, we are so accurate by using the first 7 terms. It's ridiculous. Now, notice I never found S sub 7. I could do that if I wanted. I could out of the first 7 terms. But this just asked me for the error. It didn't ask me for S sub 7. It asked me for the error, and that's A sub 8. This isn't complicated. I just find the 8th term to find the error in truncating at the 7th term. Everyone write down that answer? That's a very small error. Okay? And then tomorrow I'll explain to you how we can find the error between a Taylor polynomial and the real function. So I'll draw a quick sketch of what we're going to do tomorrow, but this deserves a whole day. So we've been talking about how, like e to the x over 2, right, can be modeled by a polynomial. Let's say I told you, hey, between 0 and 10, just how bad does what's the worst possible estimation of blue versus, with red versus black? Like, where's the biggest gap, and how big is that gap? Well, you can see the biggest gap here is probably right in here, way over here at x equals 10. That's when the gap is most wide, right? This is the point, x equals 10 would be the point where the red approximates the black the worst. And we would like to find the length of that little gap right there. That's sort of like a maximum error. Taylor polynomial function, what's the gap there? What's the biggest gap we've got between 0 and 10? It's right there. What is it? How long is it? So a guy named Lagrange figured that out. So tomorrow I'll teach you how to find that little gap right there. Sometimes he's all the way on the right. Sometimes he's sort of in the middle. Sometimes he's on the left. But we're going to find that little gapper. And we're going to say, hey, look, Taylor polynomial does a good job approximating. All the errors are less than that little green guy. Okay? All right. So we'll stop there today. That just tells you what we're doing tomorrow, right?